let G be a group and let little g be an element of that group. What we want to prove is if Z is an element of the center, then these inner automorphisms are the same. You got to do the exact same kinds of thought processes that I was just showing you the last 20, 25 minutes. You're trying to show two functions are equal. How do you do that? You got to show that for any input, an arbitrary input, the outputs are the same. Again, we won't do a full polished proof, but let's just think about the scratch work. Maybe I want to start with a more complicated one. G sub Z, or phi sub Z times G of an arbitrary element X. What does that equal? By definition of an inner automorphism, the inner automorphism induced by this element Z times G, that's Z times G times X times Z G inverse. Use the Sachs-Schurz property, which is true even if Z were not in the center. But then because Z is in the center, I can rearrange. I can bring the Z inverse over to the front. Since the Z is in the center, it commutes with everything. And Z times Z inverse is E. And E times anything is that anything. And we are effectively done. That's the same as phi sub G of X. Since X is an arbitrary element of capital G, and we've shown these function outputs are the same for that arbitrary input X. This is true for all X and G. That's enough to say these functions are the same, because two functions are the same if they have the same outputs for any given input over a given domain. The domain in this case is capital G. By the way, it is kind of arbitrary that the Z here is on the left. It could have been on the right. This is also equal to phi sub V times Z, since Z is in the center. This other statement here is kind of like the converse of the one we just looked at, though not quite. It's not stated in a way that's quite like the converse. Let G be a group and let G and H both be in capital G. If you assume the inner automorphisms are the same, show that H inverse G is in the center. By the way, since H and G are arbitrary elements, I also could say G inverse H is in the center. And that also makes sense when you think about relating those elements in the fact that these are actually inverses of each other by the Sachs-Schurz property. H inverse G inverse would be G inverse H inverse inverse, which would be G inverse H. And Z of G, the center, is a subgroup of G. So now you're assuming the functions are the same. You're assuming you know that for any given input, these outputs are the same for all X. We're assuming this is true for all X and G. That's what this assumption up there means. What does that mean? Use the formula for inner automorphisms. It means Gx G inverse equals Hx H inverse for all X and G. I'm going to keep that quantifier, that for all X and G, the entire way here. What's my goal? My goal is to show H inverse G is in the center, that it commutes with an arbitrary element, call that element X. Is this equation equivalent to that? Yes, though it's a little tricky to see. I see a G there. I kind of like maybe an H inverse on its left. So maybe I should multiply both of the sides of this equation by H inverse on the left. If I do it to one side, I got to do it to the other side. And I see something happy. I see an H inverse and an H next to each other. So that becomes this, which simplifies to this. And if I want to, maybe for emphasis, I could rearrange the parentheses here like this. I see an H inverse G there, to the left of the X here, and an H inverse to the right of the X there. How do I get rid of that G inverse, and how do I get a G to the right there? Multiply both sides now on the right by G. H inverse G, X, G inverse times G, maybe parentheses for extra emphasis at the start, is X H inverse G. But yeah, the associative law works. H inverse G, X. I can rearrange parentheses like this and also like this if I like. That's E. This product is X. Therefore, H inverse G times X equals X times H inverse G. And this is true for all X and G. H inverse G commutes with an arbitrary element of capital G. Therefore, H inverse G is in the center. So yeah, it's abstract to the extreme, you might say. Easy to get confused, but also once you get it, it's like, again, I emphasized the other day, you do the only thing you can do, and you're kind of crossing your fingers, hoping you don't make a mistake. And if it's kind of like set up to work, that's what happens in abstract math situations like this, where you've got things that are true, at least, is they almost are set up to work.